Hello students, welcome to EPG Pathshala. I am Dr. Maimuna Akhtar from School of Pharmaceutical Education and Research, Jamia Hamdard. Today we are going to discuss about a module, Inductive Coupled Plasma Atomic Emission Spectrometry under paper Atomic Spectroscopy. In this module, we learn about basic inductive coupled plasma atomic absorption spectrometry system, the various components which are employed in ICP-AES system, how sample is prepared and introduced into ICP system, and what is plasma torch and its working, how different spectral lines of interest are separated and data is collected and stored, what type of interferences are faced in ICP-AES, and what are the weaknesses and strength of the technique. So in previous modules, we have already discussed about the atomic emission spectroscopy, and by now you are well aware that in atomic emission spectroscopy, flame is used as emission source. So it was in mid-1960 when plasma-based instruments were developed by Greenfield et al. They were current and microwave induced systems generating plasma. These had limited use because of the interference effects and plasma instability during analysis, due to which flame-based spectrometry instruments dominated the market of metal analysis at that time. The limitation of the first plasma-based instrument were overcome by use of an inductively coupled plasma. The inductively coupled plasma optical system became popular in 1980 due to low cost, less time requirement and labor saving. It also had advantage over FBIS system, that is usually requires unique radiation source and a unique lamp for each individual element system. They analyze a single element at a time and were unable to easily analyze metalloids, as they were able to analyze about 60 different elements at the same time with a single source, that is plasma. Therefore, most commonly used instruments are inductively coupled plasma atomic emission spectrometer and inductively coupled plasma mass spectrometers these days. So how this ICP-AES works? Their operation basically relies on the interaction of molecule with electromagnetic radiations. As you may be knowing about nuclear magnetic radiations, where the molecules interact with the electromagnetic radiation. The principle or theory of this ICP is more or less same. However, they differ from flame-based spectroscopy methods because of low temperature, that all the atoms or elements present in the sample are not excited, especially in case of polyatomic compounds, in the way atomic species are treated and excited. In it, the sample is subjected to temperature which is quite high, 6000 to 10,000 kelvins. As a result, effective excitation, more than 90% of approximately 60 elements can be achieved, in compared to the flame-based, where the temperature limitation is 2000 to 2500 degrees centigrade by using different mixture of the solvents or fuels. The intense heat prevents formation of polyatomic species and thus increases detection limit for many elements. This technique is effective in case of some non-metals also. The emission of photon occurs where normal valence electron relaxation by photon emission, that is resonance fluorescence. In spite of eliminating many problems, plasma-based systems are not free from interference. The interferences are caused due to excitation and subsequent emission of spectral lines from elements of not interest in the sample, as well as from the argon added to facilitate plasma generation. However, in modern instruments, this has been overcome with specialized sequential monochromators. As compared to flame-based spectroscopic measurements, ICP AAS offers high sensitivity, high selectivity between elements and large dynamic range. Shows you an overview of the basic ICP AAS, where the sample is kept in one flask and is drawn through pneumatic pump to a nebulizer, and a spray is made, and simultaneously argon is supplied as a carrier gas, and it is then fed into the plasma torch, wherein due to the radio frequency generator the nebulization occurs. It is then fed to the primary slit, and which is followed by collection in the detector and supply to the data analysis. Components of ICP-AES. There are two basic components in addition to other parts which are present in all kind of spectroscopy, especially atomic absorption and atomic emission spectroscopy. That is inductively coupled plasma source. It has largely changed with exception of change in monochromator for checking interference and the atomic absorption detector. Since the invention of ICP, source has largely been unchanged with the exception of change in monochromator type for handling of interference phenomena. The sample solutions may be digested soil or water or other solid materials that are acidified to prevent the adsorption of metal present in sample or on sample bottle or instrument tubing or glassware. 2 to 3% of nitric acid is used for acidification before introducing into the plasma. The solution is introduced to the nebulizer via peristaltic pump and a Tygon tubing attached to automatic sampler. A peristaltic pump helps the sample through the system by sequentially compressing flexible tubing. The rate of sample introduction into the plasma changes as peristaltic rollers moment increase or decreases. The argon gas carrying the sample through the sample aperture of the nebulizer creates micromolar sized particles that form a mist in the nebulizer chamber. Large sample droplets are collected and are removed from the drain. Mist, that is small sized particles, travel with the argon flow and enter the torch. In plasma, evaporation, atomization and excitation, or you can say ionization, occurs at temperature approximately 10,000 kelvins. As the excited or ionized molecules leave the plasma, excited electrons relax and an emission characteristic of the electron transition of the element is observed. The radiations emitted from the sample enter the monochromator through a small slit where the wavelengths are separated by prism or gratings before they are being captured by detectors. The configuration of the monochromator is important to avoid the spectral inference that may still occur. Some systems use multiple PMTs to monitor each wavelength simultaneously. Data from the detector are processed by a computer because multiple wavelengths are measured in an ICP-AES system at the same time. So before performing the experiment, the sample preparation is important in case of ICP-AES. First is predominant form of sample matrix, that is liquid sample. It is acidified with water or solid is digested into aqueous form. For digestion of solids, the sample is mixed with lithium metaborate in 1:9 ratio and the mixture is melted at 900 degrees centigrade. The residue obtained is dissolved in nitric acid solution or with nitric acid or hydrochloric mixture or perchloric or hydrofluoric acid. That means any of the acid can be used for digestion. The microwave digestion has also been employed, which basically is acid digestion in controlled temperature and pressure vessel. The solid samples are dried, ashed if necessary, and reduced to less than 74 microns prior to distillation process. For precision and accuracy, most of modern ICP systems come with automatic samplers, which consist of a computer-controlled robotic sampling arm that draws liquid for each sample via peristaltic pump. The samples are then pumped into the nebulizer and sample chambers to create a fine mist of liquid particles. Larger water droplets that condense on the side of the spray chambers are removed by the drain out of the chamber by the same peristaltic pump while smaller droplets move with the argon flow, that is a gas used, and enter the plasma. After going into the nebulizer helps to ensure that the sample enters into the plasma at a uniform flow rate and with specific droplet size. Droplets that are greater than 5 μmicron in diameter are likely to interfere with plasma stability. This figure is an overview of sample introduction and the nebulizer chamber, which is of pneumatic style. The sample inlet from the autosampler and the pneumatic pump withdraws the sample, feeds into the nebulizer with the help of the argon gas, and from which it is supplied to the plasma torch. The most commonly used nebulizers are pneumatic nebulizers, ultrasonic nebulizers, grid nebulizers. We have touched these nebulizers in modules covered under instrumentation part of the atomic absorption spectroscopy. Argon is most often used as gas in various nebulizers as it is used in generating the plasma. But other gases can also be used. For example, for samples containing low concentration of total dissolved solids, concentric pneumatic nebulizers are used, whereas when high suspended solids and dissolved solids are there, Babington pneumatic nebulizer are used. Ultrasonic nebulizers provide more sample delivery to plasma and they improve detection limits. Grid nebulizers create fine mist by placing a grid in front of the argon flow. But since nothing comes without limitations, ICP system also faces some limitation with respect to nebulizers. The particles of micrometer size clogs the tip of the nebulizer and they must be removed by filtration or by centrifuge. Presence of high total dissolved solids may cause accumulation of solid in the tip of the nebulizer as well as in the sample chamber and on the sampler cones located just after the plasma. Most ICP instruments limit the sample TDS level to approximately 0.1 to 0.2% salt by weight. Coming to the introduction of sample, liquid injection is the most common form of sample introduction. Other forms of sample introduction include direct insertion of 10 to 30 milligrams of sample on a graphite probe into the plasma via the normal nebulizer entry port, or injection of the effluent from chromatographic separation system, especially from high performance liquid chromatography, supercritical chromatography and ion chromatography units. So coming to inductively coupled plasma torch. So for purpose of metal analysis, inductively coupled plasma system is important. The purpose of torch is to evaporate the solvent, usually which is water, from the analyte salt, convert the sample to small atoms, or you can say in other words, atomize the atoms in the salt, break the ionic bonds and form gaseous state atoms, and excite those atomized atoms. ICP-AS needs only excitation for which argon plasma is sufficient. Extreme temperature of argon plasma used in modern ICP systems cause complete excitation of the most atoms in the sample. Torch is composed of 3 concentric quartz tubes through which the center of which the mixture of sample and the argon gas is aspirated. The argon gas generated plasma passes through the middle tube and the third outer tube is used for circulation of argon gas to keep the quartz torch cool. Figure shows the plasma torch and plasma temperature at different points of the torch. So how this torch works? This torch is in place of flame in atomic emission spectroscopy. That means in place of flame that is used in atomic emission spectroscopy, here torch is used. So how it works? Radio frequency electric current and associated magnetic fields interact to generate the current. Ionization of argon gas happens, which is sparked by the Tesla coil. The acceleration of ions and electrons by magnetic field occurs, which is followed by transfer of energy from the electrons to the gas by collision, so the gas is heated up. A production of high concentration of both excited atoms and ions takes place. So after igniting the torch, samples are introduced into the system through the nebulizer. The solvent evaporates and salts are formed as the sample enters plasma. It decomposes as they go into the hotter portion of the plasma. The valence electrons on the sample atom are excited or the atoms are ionized. The high and intense heat of the plasma makes sure that only atoms or ions are present in the plasma. They also help in higher detection because of complete excitation of atoms. After excitation, the atoms exit the plasma and get cooled to 6000 kelvins and relax by emitting a characteristic photon. The light emitted is allowed to pass through one of the monochromator or detector system. The operational cost of the system depends upon the consumption of rate of argon gas. In older systems, 20 liters per minute of argon gas was supplied, whereas in all modern systems, the use has been reduced to below 10 liters per minute. The portable systems use far small flow rate and many labs use cryogenic source to reduce operational cost. For separation of the emitted photons of interest, monochromators are used. And separation is important since we have to study the isolated wavelengths only. The position of the monochromator entrance relative to the plasma source is an important factor in isolating the wavelength of interest. The monochromator can be aligned at an axial or radial position, as shown in the figure. The axial design gives better detection limits and intensities, whereas radial design allows photon to move from the side of the plasma. Therefore, it is the call for the analyst to choose to monitor the emission from the radial angle or axial angle, depending upon concentration of the analyte in the given sample. Changing the angle of observation can potentially avoid additional sample preparation such as dilution. This shows you the radial versus axial design of the ICP. In radial, the traditional side view is there. It is good for concentrated samples, whereas axial dilute samples and shows low sensitivity with shift detection range is lower. The detection can be done in many methods or many ways. One is sequential, the other is simultaneous multi-channel, or we can use Fourier transformer systems. In first two cases, that is sequential and simultaneous multi-channel methods, all wavelengths enter and are dispersed by prism or grating monochromators and are then transmitted to the detector. That can be a photomultiplier tube or CCD. In the third option, no slit or monochromator are required. It produces a spectral separation by capitalizing ion constructive interference technique. As a result, creates better detection limits as more intense radiation reaches the detector. They also have higher spectral resolution. In ICP AAS systems with sequential monochromators, only one element could be detected at a time, and hence they have limited use while analyzing multiple elements, because grating systems has to be rotated to direct the appropriate wavelength to the exit slit of the monochromator and in the PMT. The technique provided superior detection limits than FBSI, but it was as low and laborious as FBS, so that multiple elements can be detected at the same time, and following design changes were made. A standard grating monochromator separated the photons based on wavelength and directed the photons of interest to specific exit slits. That means more than one exit slit was used. Then a single movable detector rapidly moving from one slit to the other analyzes photons of various wavelengths. A standard grating monochromator separates the photons based on wavelength and directs the photon of interest to specific exit. Then a single movable detector, as shown in the figure, rapidly moves from one slit to the other, analyzes photons of various wavelengths. On the left hand side, a single detector sequential type monochromator is shown, and on the right hand side a Rowland circle ICP-AES system has showed, wherein you have number of slits which direct wavelengths of different numbers to the detector, which is movable. Recent advances use a combination of two monochromators, one prism and one Ashley grating, or one conventional grating monochromator and one Ashley grating. Removes the exit slit and places a charge coupled device, multiple element detection system or charge injection device in the path of the separated wavelength. This figure shows you a multiple monochromator ICP-AES system with a Ashley grating and a monochromator, accumulating lens and prism to capture the wavelengths of interest. So when performing any experiment, any analysis, data collection is the key for success of the experiment. If the data collection is not done properly, your experiment is lost. So for single element detection, a simple chart recorder or digital display is sufficient for data collection. Whereas in case of advanced systems, advances have been made in data collection also. So with advances in ICP-AES technology, computers became an important part of the system. They are used to control the automatic sampler and the instrument and are also used for data collection. Data collection systems are divided into two parts. One is method file, that is to run the instrument, that's all the data that is related to running of the instrument. And second is sequence file. This tells the instrument where a sample is in the sample tray, when to run it, and where to store the collected data file. So no system is devoid of interferences. ICP is also not devoid of interferences. However, the interferences are greatly reduced over those created in the other systems. Nebulizer, ionization, chemical and spectral interferences are all present in ICP systems. The spectral interferences in ICP systems are most prominent than any other type of interference. So any physical or chemical difference between reference standard and sample results in nebulizer interferences. That means the sample and reference standard should be exactly in same format or same concentration, same solvent systems to avoid the matrix effect or nebulizer interference. Matrix effect or interference are also seen if there is inconsistent presence of matrix salt and organic compounds between the sample, or it may be due to different viscosities and surface tensions of the liquid used to make the solutions. These problems can be corrected by use of standard addition calibration technique, but they cause increase in the operational cost, primarily due to labor cost. Nebulizer interferences are less prominent in case of samples are of low ionic strength. Due to high temperature of the plasma, inert atmosphere of the argon plasma, and long residence time of sample in the plasma, chemical interferences are less or practically non-existent as compared to its contemporary techniques. Ionization interferences, for example, in direct arc and microwave produced plasma, usually only occur for easily ionized elements such as alkali and alkaline earth elements. The net result of ionization interference is an increase or decrease in the intensity of emission lines for these elements. Few ionization interferences occur for these elements in ICP-AES. Spectral interferences can be common in high temperature plasma as opposed to flame-based systems, given the complete excitation and subsequent emission of all compounds in the sample, including argon. Spectral interferences can be divided into two categories. One is spectral line coincidence, which occurs when resolution of the monochromator of the system is poor to separate the analyte line from matrix line. The use of Eshel monochromators with high resolution eliminates this interference. Second cause occurs when a wavelength of interest overlaps completely with a nearby broadened line wing. and it can be solved by monitoring a secondary emission line for that particular element. Most instruments use a background correction technique to overcome this type of interference. Spectral continuum occurs when stray light results from the recombination of electrons with argon ions in the plasma that emits multiple intense lines. And this can be avoided in instruments by adjusting the temperature of the plasma or monitoring alternate lines. Stray light from matrix emission can be avoided by use of high-end optical compounds such as solar blind PMTs. The ICP AES systems have a number of strengths over to its contemporary techniques. One, the excitation of most of the elements take place and therefore can directly detect most cations, and it can also detect some of the anions. Prevents the formation of most interferences. For example, breakdown oxides and eliminates most molecular spectral interferences because almost all of the sample is excited. It can detect as low as parts per trillion concentration of some elements. Selected elements can be determined simultaneously, rapidly, and with ease. Sequential determination of selective elements is also possible. It has good linear range up to hundreds of parts per million for alkalis and is suitable for routine analysis of multiple samples. Not every system is perfect. We all know that. So therefore, ICP-AES, inductive coupled plasma atomic emission spectroscopy, also has some weaknesses. The weakness is the low level of the alkalis. It cannot be used for detection of the alkalis if the level is below 1 to 5 parts per million. Another problem is the matrix problem. The matrix is a part of you can say system which is used in addition to the sample preparation. A suitable standard is required for every run, and that makes it cumbersome. And the only elemental data is provided. No direct structural information is obtained. For that reason, the inductive coupled with mass spectrometer has been used. So students, let's now summarize what we have learned in this module. In this module, we learned about development of inductive coupled plasma atomic emission spectrometry as a useful technique for analysis of over 60 elements. We also learned about the instrumentation, sample preparation, plasma torch and its working, how the spectral lines of interest are separated and how data is collected and stored. We also looked into the interferences that are faced in ICP-AES system. Its strength and weakness were also discussed during this module. Thank you.